is actually, there are 5 sections in it, but we are only covering 4 of them. So this is the last section that we are covering in this chapter. What we're going to do after today is take a couple days of reviewing all this probability, because really we've been practicing like one technique per day, and I want to give you guys a chance where everything's kind of intermingled and you have to think about what I need to do when, instead of just knowing, well, today I'm adding probabilities and today I'm multiplying probabilities. So I'm going to teach this lesson today, then tomorrow we'll do a review day, and Monday will be a review day. So then we'll do a quiz over chapter 5 on Tuesday next week. So we'll have 2 days of just straight reviewing this stuff, and then a quiz on Tuesday before we start chapter 6. So we've talked about the OR statements, and OR means we are going to do what with our probabilities? Add them. And then we talked about our AND statements. And means we do what with the probabilities? Multiply. Now the thing we looked at yesterday, for all of those, in order for us to just be able to multiply our probabilities, what had to be true? I couldn't do it for, they had to be independent. Okay, so today we're going to look at what we do if they are not independent. So a conditional probability. When you see these, you'll see the probability of F, then there's a vertical bar, that means given E. So we talked about situations where they're totally independent. Even if I know that you have my class first hour, does that change the probability that you are wearing flip-flops today? No. But what if I said the probability that you are wearing flip-flops today and the probability that it's snowing? Will snow, knowing that it's snowing, would that change the probability you would be wearing flip-flops? Yes. So that is when we have to look at this conditional. Because if I already know one thing has happened, if I already know it's snowing, what's going to happen to the probability that you wear flip-flops?
Go down.
It's going to go down. So when you know one thing has happened, it will change the odds of the other. So that's when we have a condition, the conditional probabilities. So let's look at an example. So I am going to roll a die. First question, if I just roll a dice, what is the probability that you get a 4? 1/6. There's 1 4. There are 6 total sides. Okay, second question. What is the probability if we roll it, but I am told the outcome is an even number? So I want to know what's the probability of a 4 given that I already know it is even. Okay, if I already know it's an even number, how many even numbers are there? 3. How many of those are 4s?
1.
So if I already know it's an even, then there's a 1/3 chance that I rolled a 4. Do you guys understand the difference between those 2 scenarios?
So, if it said that you rolled a 4 and it was odd, would you automatically use 0?
So the probability of rolling a 4 given that it was an odd number. So there are 3 odd numbers, but how many of those are 4s? None. So it would be a 0. It would be impossible. Other questions? So when I found that conditional probability, what changed in my fraction? My numerator was still 1, but what part of that changed? The denominator. And how did I get my denominator? Where did that come from? When you had your condition, that changed my total. So in general, the probability of F given E equals the probability of E and F divided by the probability of E. We could also be looking at complements with this, the same holds. This is all on your formula sheet, so it's up to you if you write it down in your notebooks. You can think of it as also, if I tell you that E doesn't happen, then your denominator would be the probability that E, doesn't happen in the top, not E and F. So what I need you to realize is that if you have a condition, the denominator changes. When you have a given, your denominator becomes that piece. Okay, so it's no longer out of the whole. It's out of just those people that meet that condition. So we'll try a few examples of calculating these conditional probabilities. So a survey was conducted in which 1,017 adult Americans were asked about their beliefs in a higher power. And so they broke it up into the belief and the region of the U.S. So part A, what is the probability that a randomly selected adult American who lives in the East believes in God? So when you do this, you have to think about your condition. Okay, what do we already know?
They live in the East.
So my given is that they are in the East. So we're trying to find the probability that they believe given they are in the East. So when I set this up, my denominator is from my given. So it's my East. So what do I need to do?
Add up everybody in the East.
I am not looking at everybody in the table. I am only looking at those people in the East. So if I add those up, then my numerator, I'm still only looking at that portion of the table because I already know they're in the East, so I know I'm in that row. How many of those believe? And we get 0.8. Yes, ma'am.
How did you know believe went first?
That we were trying to find probability that they believe in God. What we knew is the who lives in the East. So I'm already telling you that that is what we know. Yes.
So say that it didn't say who lives in the East, we would just do it how we have been. We just
Yeah, if I just said what's the probability that they believe in God, then it would have been the total ones if you add up the believe in God and then divided by everyone out of the table. All right, so far so good? All right, let's look at B. What is the probability that a randomly selected adult who believes in God lives in the East. What did I change here?
The order of the sentence.
What do I know for sure at this point?
They believe in God.
Okay, so that is my condition that I know. And I'm trying to find the probability of what? That they are.
Since they live in the East.
So, when I set up this condition, the given, that is the piece that I already know. So that is the only part I'm looking at. So I'm only looking at this column of my table. So when we divide our fraction, the denominator comes from that column of the table. So you add those up. And then, only looking from those, how many are in the East? And we get 0.2592. Okay, so can't stress this enough. When you have a conditional, the denominator is your given. So whatever we are given, that's the denominator, and then that is the only part of the table we are looking at. Let's look at another. So in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also, in 2005, 16.6% of all murder victims were 20 to 24-year-old males. What is the probability that a randomly selected murder victim in 2005 was male? So I'm finding the probability of a male given the victim was 20 to 24. Okay. My denominator is my given. So what is the 20 to 24? What's the probability that you're between 20 to 24?
15.1.
Of those, so of the 20 to 24-year-olds, how many were male? So if we divide those, we get 0.8691. So if we know that the victim was between the ages of 20 to 24, there is almost an 87% chance that it was a male. Questions on that one? So this leads us into how to find the probability of E and F if they are not independent. So when they are independent, knowing one didn't change the probability of the other, so we just multiplied. But if they are not independent, if I know that victim just is 20 to 24, did that change the probability that it was a male? Yes. So if it's not independent, probability of E and F is probability of E times the probability of F given E. So you're still multiplying the probabilities, but if you already know the first, you have to do the conditional. It works the other way too, so that would be the same as the probability of F times the probability of E given F. So this is on your formula sheet. It only has the first one, but E and F can be interchanged in there. So the second option works too. So, same problem as last time, but I'm asking a different question. Last time we knew the victim was 20 to 24, and from that we had to figure out the chance that they were a male. This time I'm just asking, what is the probability that we have a 20 to 24-year-old male? So the probability of 20 to 24 and male. Okay, and means multiply, so I know I'm going to be multiplying two things. If we think about our formula, we have two options to do the probability of E times probability of F given E, or probability of F times the probability of E given F. Let's look at the conditionals that we have here. We have the 19.1% were between the ages of 20 to 24. So that's the probability you're between 20 to 24. Then the second one would have to be the probability that you are male given you are 20 to 24. So the probability of 20 to 24 is 0.191. If we already know that you're 20 to 24, what was the probability that you were a male? That's what we found out in the last problem. And I also just restated it here. So now if we multiply those, one 6 5 9 7, so 1 6 6 0. Is that okay with everybody? Yes.
So did we also already find that in the last paper?
Yes, that's where I just pulled that number from the last example. Alright, let's keep looking at these. Suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. The plant manager receiving the circuits randomly selects 2 and tests them. If both work, she will accept the shipment. What is the probability that the plant manager rejects? Okay, so she accepts it if they're both good. She rejects it if they're not both good. So that means if the first one is bad and the second one's good, or the first one's good and the second one's bad, or if they're both bad. Would it be easier to find the probability that she accepts or rejects? Accepts. And then how could you get the probability she rejects from that?
Subtract that.
So, the probability that she rejects would be 1 minus the probability that she accepts. They're complements. You can't do anything else. Your two options, you either take it or you don't. Alright, so we have to find the probability that she accepts. And what will make her accept it?
If they both work.
So, probability the first one works and the second one works. Okay, so I'm kind of going off side note. This is what I need to do, but first I have to find out the probability that she accepts it, and that only happens if they both work. So, what is the probability the first one works? How many good circuits are there?
90. Oh, no, 95.
95. There are 5 bad ones out of 100, so 95 of them are good. So the probability the first one works is 95 out of 100. Now, you had 100 of them. 95 were good. You have selected one good one out. How many good ones are there left?
94.
94, because I already took one of the good ones out. And how many total circuits are there? 99, because you already took out that first one. So that's the conditional. That second probability changed. It wasn't still 95 out of 100 because I already took that first one out. So now there's only 99 left in the box, and 94 of them are good. So if we multiply those, we get 0.893. Now that's the probability that she accepts. So the probability she rejects is 1 minus that. We get 0.107. Oh, hold on. I mistyped something in my calculator. That's not true. I apologize. That's wrong. This should be 0.9020. So you get at 0.098.
What did you put in wrong? Because I got the same thing.
I accidentally typed up 94 over 100 instead of 99. Yes, ma'am. I did one at a time. So you have your box of 100 parts sitting in front of you. And you're going to take one out and test it. And I want it to be a good one, so because I'm accepting it. So there were 95 good ones, so 95 out of 100. Okay, we're good. I took that one out and I set it to the side. So then when I go back to select my second part, how many are in my box? 99, because I've already taken that one out, and I want another good one. So there were only 94 good ones left. So she didn't take it out, look at it, and then stick it back in. If she had put it back in, then what would have been the probability the second time? Still would have been 95 out of 100, wouldn't it? If I put that part back in the box. But I didn't. I left it out, and then I took another one.
How do we know if that first part was going on? Or does that have like any effects?
We wanted to find the probability that she accepted it. So for her to accept it had to have been good. Other questions? Yes.
Okay, so you took those two and you multiplied them together. But, like, how is that really using the formula? Because the second one isn't, like, using a given.
Okay. It is in a way. So the formula, so we are finding the probability the first works and the second works, right? So if we use the formula, it's the probability of the first times the probability of the second one given the first one worked. So the probability of the first one, that's our 95 out of 100. Since I've already taken out that first one, my denominator is now only 99. If you were just doing independent, it would have still been 95 out of 100. But because we already took out a good part, now there's only 94 good parts out of 100.
So it's saying, like, given that we already took one out, we can make the same.
Yes. Other questions? Those are thinking. I like it. Let's do some more. Okay. Of 3,215 individuals surveyed, 130 agreed to a recent bond issue. Part A. So suppose we randomly take one person. What's the probability he or she agreed?
What are we talking about
My survey?
here? No, but what's the bond?
I don't know. Whatever it might be, whatever a recent bond issue is. I was trying to be less wordy than your both examples and not give you all the extra information you don't need. See, now you guys want more information. All right, so if that's all I know, what would I say? This isn't a trick question. Probability that she agreed. How many people agreed? Out of how many total? Okay. So we get 0.0404. Okay, part B. If two individuals are selected, what is the probability they both agree? So that's the probability that the first agrees and the second agrees. And means multiply. Okay, so the probability that the first person agrees is still 130 out of 3250. Alright, but I've already talked to one person and they agreed. So now how many people are left for me to talk to?
3,214.
And how many of those agree? Okay, so that's the conditional because I've changed that probability the second time given that I'd already talked to one person that agreed. And we get 0.0016. So there's not even a 1% chance that my two people would both agree. Because there's only a 4% chance anybody agrees. Alright. Let's say I compute the probability assuming independence. So I just did this to illustrate the difference between independent and dependent. Part B, we treated it as those things being dependent. They're not independent. I already talked to the first, I'm going to talk to a second. But part C is like saying, okay, I'm going to number my people from 1 to 3,215, and I'm going to randomly draw two names out of a hat. Is it possible that I could select that same person twice? If let's say I just take them out, I call them, and I put them back in, and then I pick it back up. That would be independent, because once I talk to that first person, I put them back in my hat. So if they're independent, what's my probability each time? So what changes with that independence is just that second fraction. That's what I wanted to show you here. And so we get 0.0016. If we had kept more decimal places, we would have seen the difference. The last one was 2.3. After that, this is 3.5. So a slightly higher chance, but not much. All right. I am going to put an example up here that I would like for you guys to try on your own. So, part A, we want the probability that two are defective. So how many defective pieces are there?
50.
Out of how many total?
9,950.
We shipped 10,000, so 10,000 is my total. Then when I said using conditional, that means my second one is probability that this one is bad given that the first one was bad. How many total do we have if we've already removed one?
9,000.
Yeah. And then out of those, how many are bad?
49.
49, yeah.
Yeah, we did it.
So I was like, oh,
that's
it's
right.
wrong. Yeah.
Yeah, so it gives you that E -5. That means you move your decimal back 5 spaces. So there's 4 zeros, 2, 4, 5. So a very, very small chance. Which if you think only 50 out of 10,000, are there very many bad ones in there? No, we have 50 bad ones and 9,950 good ones. So it's not very likely that we're going to select 2 bad ones in a row. If we treated this as independent, that means you take your first, you select it. If they're independent, then you have to throw it back in the pot and then select the next one. So what's the probability of the second one if I put the first one back?
15 times.
And you get slightly higher chance, but not much. Last example. So I'm really trying to practice using our formulas and manipulating those. The first one, I want the probability of A and B. We have 2 options. The probability if they're independent and then our regular. Did I tell you that A and B were independent? No, so we have to use our conditional, which that formula is the probability of the first times the probability of the second given the first. So the probability of A is 0.7. Probability of B given A is 0.4. So you multiply those and what do you get?
0.28.
Part B. This time, I kind of changed things up. Now, the A and B formula I just used had B given A. If I want A given B, what would I have to write for my formula? The probability of B times the probability of A given B. Because I told you that A and B can be flipped. The first and second one can be flipped. So then we plug in what we know. Probability of A and B is 0.4. Probability of B is 0.5 times probability of A given B. So how do you find that probability? Divide. So 0.4 divided by 0.5 gives us 0.8. The next one. I gave us a lot of information here. A, B, A, or B, and I'm asking for A given B. The only way to find A given B is that formula we just used. Probability of A and B equals the probability, since I want A given B, it'd be the probability of B times the probability of A given B. But do I know the probability of A and B? No. How can I get it? We have to find one of these things before we can use this formula, right? I gave you the probability of A or B. Do we have a formula for A or B? Look at your formula sheet. What is it? Did I say they were mutually exclusive? No, so you have to use the general addition formula. So it's probability of A plus probability of B minus the probability of A and B. So if I start here, A or B is 0.66. Probability of A is 0.4. Probability of B is 0.3. So if you subtract subtract, you have your 0.66 minus your 0.7, divide by -1, so the probability of A and B is 0.04. Now we can come to our second formula and plug that in. So to find the A given B, what are we going to have to do? Divide. So these are just straight using your formulas off your formula sheet. You just have to figure out what we have and where we can plug it in. So this time I had to use two formulas because of what I was given. The last example. I gave you the A or B, the A and B, and the probability of B. Oh, sorry, I kind of wrote up. That's the probability of B complement. So the probability of not B. So how do we find the probability of B? You do 1 minus the complement. And you get 0.6. How could I get the probability of A?
Is it not 0.6?
That's B, because this, what I gave you, was not B.
Oh.
Can we use the OR formula? Probability of A or B, probability of A plus probability of B minus probability of A and B. So A or B was 1. I don't know the probability of A. Probability of B we just found was 0.6. A and B was 0.7. This is a bad problem. This doesn't even work, does it? Oops, can I adjust something? Sorry, make this probability of A and B, let's make that a 0.3. Sorry about that. Okay, so then subtract your 0.3, so the probability of A is 0.7. So then if I want the probability of A given B, we can use our AND formula. That's the only formula that has that conditional in it. So we would have to do the probability of B times the probability of A given B. A and B is 0.3. Probability of B is 0.6. Divide, and probability of A given B is 0.5. So those types of problems are just getting us used to manipulating the formula. Okay, I need you guys to listen carefully here. So I'm getting ready to put the assignment up. Same directions that we've been using on all of these. So if it says find and interpret the probability, you only have to find it. If it asks the question and the only thing it says is interpret, then you have to interpret. One of these does tell you to make a tree diagram, and I put on here in my notes that tree diagram is optional. We did one where we did like probability of 3 children and 2 boys and a girl. Remember when we start out boy, girl, and drew the little things, branches coming off? That's optional. You don't have to do it on that one. This is going to be due on Monday. Tomorrow, we have a review day. You will have time to work on this, but I'm also going to give you a review worksheet tomorrow. So you'll have 2 things tomorrow, but a whole class period to work on them, and then anything you don't get done will be homework. So I would